Section 4.1 and 4.2, Polynomials and Laws of Exponents. The three objectives here are going to be to discuss polynomial terminology, to simplify, add, or subtract polynomials, and then to use laws of exponents when we're multiplying with polynomials. So let's start with the first part. Certain terminology are going to be very important when they're referring to polynomials. Let's take a look at some of those examples here. First, a constant. A constant is simply a number. Okay, a simple number. Now, believe it or not, sometimes a constant can be represented by a letter, but it is actually a constant. For example, if we had an equation that said something like f of x equals ax squared plus bx plus c, well, a, b, and c are numbers traditionally. When we look at quadratics, x is the independent variable. So a, b, and c would all be considered to be the constant coefficients. So this is like a constant coefficient. It's a number coefficient, constant coefficient. This is just a constant at the end. So when we're talking about just a constant, we're looking at the value that's just a number. Okay, so a numerical portion of a polynomial. Monomial. A monomial is a constant, a variable, or a product of a constant and one or more variables. For example, something like -5 would be considered to be a monomial because it's one term by itself, or -5x, or -5xy, or -5x squared y. But again, notice that these are all just one term. There could be more than one factor in that term, but they're simply one term. There are no plus or minus signs in here at all. That's how you know you have a monomial, when there's no plus or minus signs there. A coefficient. A coefficient is the constant factor in a monomial. So the coefficient is the example that we went back to here. A is a coefficient, and B is a coefficient, and C we'll call a constant. So for an example, if we had something like 3x squared, well, the coefficient is just going to be 3 in this case. Like terms. Like terms are monomials that only differ in their coefficient, okay, or they're identical in general. So let's look at an example. -5x squared y, and let's say another example, 4x squared y. Clearly, these are exactly the same, but they only differ in their coefficient. Okay, they are like terms, and because they're like terms, we can combine them using our algebraic or arithmetic operations of addition and subtraction. A polynomial is the sum of several monomial terms. So if we had something like this, okay, that would be a polynomial, because there's the sum or difference, okay, sum or difference of many monomial terms. The degree of a variable. The degree of a variable is simply the number of times the variable term occurs as a factor. So for example here, if we have 7x squared y to the third, the degree of x is 2 and the degree of y is 3. The degree of each independent variable, each variable on its own, okay, on its own. The degree of a monomial is the sum of the degrees of the variables. So the degree of this monomial would simply be 2 plus 3, which is 5. So you would add up the exponents. You would add up the exponents. If I had an example like so, let's do a new example so we can see the difference. Three x to the third, y to the fourth, z. All we need to do is add our exponents. 3 plus 4 is 7, and there's a 1 here, remember. Plus 1 means this would have a degree of 8 for this monomial. Finally, the degree of the polynomial. After simplified, this is the greatest degree of its terms. So for example, we would look at the degree of each monomial. This degree is 4 because of the 4. This degree is 2 because there's a 1 there and a 1 there. Those 1s add up to 2. This degree is going to be 5 because of the 3 and the 2 there. So what would the degree of the polynomial be? It would be 5. The greatest of them. The greatest of them. Let's look at example 1 here. Simplify, arranging terms in order of decreasing degree of x. Then determine the degree of each polynomial. So let's take a look first. Simplification means let's look for like terms. So we'll use our colors. These are like terms. 3x and -5x. These are like terms, negative x squared and positive 4x squared. And finally, these are going to be like terms here, negative 9 and positive 2. So let's go ahead and we're going to list these in decreasing degree of x. So let's start with the highest degree of x, which is in blue. We're going to have negative x squared plus 4x squared. That's like having really negative 1x squared here. So just add the coefficients. Negative 1 and 4 gives you 3. Then go to the red. We have 3x and negative 5x. So it's 3x minus 5x, or negative 2x. And then in green we have negative 9 and a positive 2, giving negative 7. Now for part B, though, we need to keep in mind that we're looking at decreasing degree of x. Let's underline our like terms again. So here I see that I'm going to have negative 8xy to the fourth, 2xy to the fourth. Those are like. Then I've got 5x cubed y cubed, negative x cubed y cubed. And then the other two terms are not like terms. But what we'll notice right away is to look at the decreasing degree of x. So this is the highest degree of x. This is the second highest degree of x, these ones here. This is the third highest degree of x. And then combining these two gives us the fourth highest degree of x. So we'll start with this term by listing that first. Highest degree of x. Second highest degree of x is in red. So we have 5x cubed y cubed minus x cubed y cubed. Remember that there's really a 1 here. So it's really like 5 minus 1. So it's going to be a plus 4x cubed y cubed. The next term that's in decreasing degree of x is this part, but there's no like term, so we'll just list that again. And then finally, in blue, we can see that we have a degree of 1 for x, so this is going to be the lowest degree of x. So we have a negative 8 and a positive 2, giving us a negative 6, and then we carry over the variable portion of the monomial. Remember, you're never combining anything to do with the variables. You're only combining the coefficients. The variables are just telling you whether or not they're like terms. Example 2. Perform the indicated operation. Find the sum of that and then find the difference between that. So let's look at the first one and underline like terms. It's going to be x squared and x squared. This is linear x, this is linear x. This is a constant, this is a constant. And the last part, the 4x cubed, we leave alone because there's no like term over here. So we're adding these, finding the sum. So we can add negative 3x squared and 5x squared. Well, let's start, sorry, I apologize. Let's start with our 4x cubed and just write that first. After that, we'll go to our x squared terms. We're going to have negative 3x squared and a positive 5x squared. Negative 3 and a positive 5 is a positive 2x squared. After that, I'm going to go to red, and I'm going to see a positive 2x and a negative 6x, yielding a negative 4x. And then my constants in blue, I've got negative 5 and a positive 4, giving us a negative 1. For part B, we want to find the difference. So what I'm going to do is I'm going to write this out first. The reason I'm going to do that is because I want to make sure we see clearly what we're doing in this problem. So really what we're doing is 6y cubed plus 2y minus 5 all minus 2y cubed plus y squared minus y plus 2. And since we're doing subtraction, it's really adding the opposite. So I'm going to go ahead and put negatives in all the spots that were positive, and I'm going to put a positive in the spot that was negative. Now I can do my like terms. Cubed and cubed. Linear and linear. Constant and constant. This y squared, or this negative y squared, has no like terms. So in blue first, 6y cubed plus negative 2y cubed is 4y cubed. The squared term doesn't have any like terms, so it's just minus y squared. Again, this comes from the minus y squared there. Then we've got 2y plus y, which is simply going to be 3y. And then we've got negative 5 plus negative 2, which is negative 7. Example 3, simplify the following. So what we'll notice is that we have to distribute our coefficient to each of these terms in each of the binomials here. So x times 4y is going to give us 4xy. And then x times negative 6 is negative 6x. Next, 2 times 2x is 4x. 2 times y is 2y. And then finally, negative 3y times x is negative 3xy. And negative 3y times negative 2 is positive 6y. Now we can see some like terms appearing. So in green, we've got 4xy minus 3xy, which is 1xy. In red, we've got negative 6x plus 4x, which is negative 2x. And in blue, we've got 2y and 6y, which is 8y. That's our final answer. Example 4 is a little tricky, but we'll go through this slowly so we can see what's happening here. Determine values of a, b, and c that make the equation true. So if we're looking for the values of a, b, and c, we're saying what are the numbers a, b, and c. So those are numbers in this problem. They're not really variables. We're looking for the numbers for a, b, and c. Now, on the left-hand side, we can see that we have some addition going on. Let's underline like terms again. Okay, so the green terms, x squared plus x squared is just 2x squared. Then the red terms, though, ax minus 2bx, okay, is going to be this. Now, this is where it gets tricky. This is what we have right here in the red. If you factor out an x out of here, you'll notice that you end up with x, parentheses, a minus 2b. But I'm going to write that the other way around. I'm going to write it as a minus 2b times x. The reason I write it that way is because now a minus 2b is the coefficient in front of x. And the last part, I have 2b plus 3a. I'm just going to put those together like this. Plus 2b plus 3a. So that's what my left-hand side of this equation ends up simplifying to. Now, on the right-hand side, I'll notice that this term is a like term with this one. This term is a like term with this one. And that this term, the constant, is a like term with this constant. So what we need to do now is really what's called equating the coefficients. And let me write out what I mean here. So I'm going to rewrite this entire thing, but with the whole thing written. So we've got 2x squared plus quantity a minus 2b times x plus quantity 2b plus 3a. And again, this is the simplification of the left-hand side. And that equals what's on the right-hand side here. Cx squared minus 7x plus 3. So take a look here. What we have is that we notice there's a coefficient of x squared that's 2 and a coefficient of x squared that's c. If these two expressions on either side of the equation are to be equal, then that 2 must be the same as that c. So we can simply write 2 equals c from the red. In blue, we've got that a minus 2b has got to be the same as this negative 7. So we can write that. But that doesn't help us too much for a and b because we still have two variables. But let's look at the last part now. The constant terms. This is a constant of 3. And this is indeed also a constant because remember that a and b are numbers. So once you figure out what a and b are, that's just going to be a number. And now we have c, and we also have a system of equations that we can solve. If we solve this system, and I'll highlight what I'm talking about right here, we can solve this simply by adding. Add straight down. A and 3a is 4a. Negative 2b and 2b cancel, so this is convenient. So this becomes a 4a, and this becomes negative 4. So when we add straight down, we end up getting 4a equals negative 4, or a is simply negative 1. So c is 2, a is negative 1, and now if a is negative 1, we can plug it back in. So let's go ahead and plug it back into the second one in this case. It doesn't really matter. So I'll plug this negative 1 in right here. That'll go ahead and give me 2b minus 3 equals 3. And therefore 2b is equal to 6, so b equals 3. So a is negative 1, b is 3, and c is 2. Okay, let's take a look at 4 rules of exponents. First, the product of powers tells us that a to the b times a to the c equals a to the b plus c. So to remember this, if you have the same base and you're multiplying things with different exponents, you keep the base and you add the exponents. For example, if we have x squared times x to the 4th, it's simply x to the 6th. The reason being is because x squared is really x times x, and then x to the 4th is really x times x times x times x, giving us 6 x's, and thus x to the 6th. The second rule is the zero exponent rule. What the zero exponent rule tells us is that anything to the 0 power is simply 1. Now, let's go ahead and prove this. If we had something like 2 to the 4th, that becomes 16. 2 to the 3rd is 8. 2 to the 2nd is 4. 2 to the 1st is 2. So what would 2 to the 0 be then? That's the question. And you can see the pattern. 16 divided by 2 is 8. 8 divided by 2 is 4. 4 divided by 2 is 2. 2 divided by 2 would give us 1. The next thing. So whenever in doubt, just simply take a look at a pattern and you'll notice that you always get 1 when you do any number to the 0 power. The third rule is a power to a power, and a power to a power tells us that if a to the b is all raised to the c, it becomes a to the b c. So when you raise a power to a power, you have to multiply those powers. Let's take a look at an example. We use the same number as before to prove the difference. Well, this is just x to the 8th based on the rule, but let's prove it. What this means is the following, really. This really means x squared times x squared times x squared times x squared, which is indeed using the first rule by adding these 4 2's together, giving us x to the 8th. The fourth and final rule is the power of a product, and the power of a product rule is similar to like a distributive rule, where you have to distribute the power to each of these terms, or each of these factors. So if we had an example like xy to the 5th, well, yes, that's just simply x to the 5th, y to the 5th. So that's an easy example. But what if we had an example like this? X squared, y to the 8th, all to the 3rd. Well, now you have to distribute it to both. So this becomes x squared to the 3rd times y to the 8th to the 3rd, which indeed is x to the 6th, y to the 24th, because we multiply those powers. So that example used power of a product, rule 4, with power to a power, rule 3. Take a look at an example of this. Simplify the following expressions. So a to the 2 to the k and a to the k to the 3. Well, this is a power to a power, so we have to multiply those powers. So the 2 times the k, multiply these, becomes 2k. The k times the 3 becomes 3k. And then if I multiply two things with the same base, I have to remember to add the exponents. So this is really a to the 2k plus 3k, or 5k. The second part, I have to remember we need to distribute this to start, because there's a plus sign in the middle there. So let's go ahead and write it out. That's distributing the first part, and distributing the second part is... Now, the first part, we have the same base, so we have to add the exponents. So what is m minus n plus m plus n? Well, the m's become 2m, but the negative n and the positive n cancel. So we'll leave that alone. Then over here, again, same base, so we have to add the exponents. Well, the n's cancel when you add them, so you're just left with the m. And at this point, this is all you can do. It's tempting to try and combine these, but remember that you're not multiplying. In the example back over here, we were able to combine these because we're multiplying, so we can add the exponents together. People have a tendency to add 2m and 3m and m to get 3m, but again, you cannot add these exponents because this is not multiplication, this is addition. You can only add things if they're like terms. These are not like terms. This is like saying x to the 2nd plus x to the 1st. You cannot add those together. Okay, there's no way to simplify that at all. Your homework from this section is from sections 4.1 and 4.2.